Thanks, Vlad, and thanks for the invitation to talk. The talk is about two-bubble wave maps, and it's joint work with Jacek Jendrej, who's based in Paris at Paris 13. I'm going to try to motivate the questions I'll consider a bit. So the object that I'm interested in is a nonlinear wave equation of semilinear type. F is you can think of it as a potential function. So df appears here as a nonlinear function of u. U is a function of t and x, where t is a real number and time, and x is a vector in Rd. And these are natural objects, natural in the sense that they arise as formal critical points of a Lagrangian action, the following Lagrangian. And so this admits a Lagrangian formulation, but and it also admits a Hamiltonian formulation. So I can view this as view this equation as a Hamiltonian system. I'll introduce this vector notation. So u vector will be the vector with two components, u and dtu, and the Hamiltonian is the conserved energy for the equation. So this is the Hamiltonian, and with this setup, I can rewrite this equation star above as dt of vector u is j composed with the Fauché derivative of the energy, dE of u, and here j squared is minus the identity. So as a Hamiltonian system, the main question you want to ask is understand the phase portrait. So I want to understand the dynamics of solutions to this equation. And of course, this is too vague of a question or too general of a question to, and what we typically do in this field is adopt a case study approach. So let me start off with an example, and I'm going to try and contrast this example with the situation I'll consider a bit. But one well-studied example of this equation is the defocusing of such equations, or the defocusing energy critical nonlinear wave equation in dimension d equals 3, which is the following equation. This is the nonlinearity is just a quintic power of u, so absolute u to the 4 times u. And this is called energy critical somehow because the natural scaling of the equation leaves the energy invariant. So the size of the energy is a meaningful object. And so such an equation, this equation is well studied, and there were breakthrough works in the 90s, Grylakis, Shatta, Struve in 93, Bahri, Shatta, prove the following beautiful theorem that if you take any initial data of finite energy, then the solution exists globally and scatters. So what scattering means in this context is that you can find, so given a nonlinear solution, it's global in time, you can find a linear wave, I'll call this u sub L for linear, which is a solution to the free wave equation. So you can find a free wave such that the nonlinear wave approaches the free wave as in the energy topology as t goes to infinity. So the nonlinear solution minus the linear solution tends to 0 as t goes to infinity. This is what I mean by my nonlinear scattering. And you can think of this as somehow that this is a dispersive equation. The nonlinearity somehow becomes negligible as time goes to infinity. And just a quick remark. So this is the energy critical case turned out to be quite a bit more difficult than the subcritical equation, which was started to be well understood in the 60s when work of Strauss, also work of Jorgen, Siegel, and Moravec. So this is a classical problem. Okay, so if a nonlinear wave looks like a linear wave as time goes to infinity, this means that it exhibits oscillatory behavior. So the kinetic energy of the wave can't tend to 0. Of the nonlinear wave cannot tend to 0 because that doesn't happen for free waves. So if you have a solution to the free wave equation, its kinetic energy, which is the L2 norm of the time derivative of u, asymptotically takes up half of the total energy of the wave. So if my nonlinear wave looks like a free wave, then and this free wave is oscillatory, and so is a nonlinear wave. So scattering solutions are oscillatory. And What I'm going to discuss in this talk is so the opposite behavior. Make a definition. So I'll say that a finite energy solution to star, which was the nonlinear wave equation I wrote on the first page, is asymptotically stationary. So in contrast to oscillatory, if its kinetic energy tends to zero as t goes to infinity. So scattering waves are not asymptotically stationary waves, right? They have non-vanishing kinetic energy. And so I'm going to try and study such solutions. And for this equation that I wrote in the first board, there's only one such solution since we have the scattering result. The only solution that's asymptotically stationary is just a zero solution. So this question, what are the asymptotically stationary waves, is trivial for the defocusing nonlinear wave equation I wrote on the previous page, given the theorem that was proved about scattering. But for certain examples of nonlinear wave equations, there are such asymptotically stationary solutions. And these are, if my goal is to understand the phase portrait, understanding these solutions is a critical component of that. Whether the solutions that I find are stable or not. And as an example to keep in mind, so there's the finite dimensional analog of the nonlinear wave equation is Newton's equation. This ODE here, okay, of course, this is the finite dimensional analog of many PDEs. But so there are examples. So the asymptotically static solutions to Newton's equation are those with vanishing kinetic energy. Typical example, those are stationary solutions or critical points for the flow. And they're stable manifolds, which are sort of non-trivial examples of an asymptotically static solution to Newton's equation. Okay. Okay, so again, I'm going to adopt a case study approach, and I'm going to focus on, for this talk, I'll focus on one particular example, but I'll try to motivate a bit. So I'm going to study a nonlinear wave equation that emits what's called a topological soliton, or topological solitons. And these, I'll be precise in a minute about which solutions I'm considering. But for the moment, just think of these as coherent solitary waves. So non-dispersive waves, and topological refers to the fact that these waves carry some non-trivial topological index. In our case, it will be the degree of a map into the sphere. So there's these are kind of much studied in the mathematical physics literature. In dimension 1, when d equals 1, there's the typical equation called the classical scalar field model. So the phi4 model is the Sine-Gordon equation. And the topological solitons for these equations are called kink solutions. And we have some results about this equation, but today I'm going to focus on the setting where d equals 2, and a classical example of a PDE emitting topological solitons is the wave map equation. So this concerns maps U, which from 1 plus 2 dimensional Minkowski space, so 2 space dimensions, taking values in the 2 sphere, and I'm going to think of the 2 sphere as being embedded in R3. This is the standard sphere. The topological solitons in this case are going to be given by finite energy harmonic maps. So this is the wave map equation. This is the box of U. The D'Alembert of U is equal to minus U times dtu squared minus gradient of U squared. And I'm going to make a symmetry reduction equation in a second, so it's not so important to remember this equation. But just I call this natural in the sense that it generalizes the free scalar wave equation to manifold valued maps. In this case, our example is very simple. It's just the 2 spheres is the target manifold. So the stationary solutions are, as I said, non-trivial finite, or there exist non-trivial finite energy harmonic maps. There's also constant solutions to this equation. And this example I like very much because these are all classified. So I know what they all are. They're explicit. So a finite energy harmonic map from R2 into S2. This set of harmonic maps can be identified with the rational functions from C infinity to C infinity. So there's a classical theorem, old theorem of Eels and Wood, which says that such a harmonic map must be holomorphic or anti-holomorphic. And so these are just the rational functions. Okay, So again, for my purposes, this version, the equation is a bit hard to study for several reasons, and I'm going to make a massive simplification. I'm going to consider what are called k-equivariant wave maps, and which means I'm going to take I'm going to only consider solutions. So r theta are polar coordinates in R2, and I'm going to only consider solutions that take the following form. Remember, this is a vector in R3, an element of the two spheres, so spherical coordinates here, and I'm going to assume that that this polar angle of the sphere u is a function of just t and r. So this is a radially symmetric function, and the map has only this angular, this type of constant angular dependence in theta. So if I impose this ansatz, if I look at solutions only of this form, the Euler-Lagrange equation, or the wave map equation, reduces to just a scalar semi-linear wave equation for radially symmetric, in fact, for u of tr, this polar angle of the sphere. And this is the wave map equation in this case. So and this looks like the equation I wrote on the first slide here. This is df of u. Here's the potential energy sine squared of u. So this is a natural example of a semi-linear wave equation, and it's well studied. So this is the energy functional, and again, this is radially symmetric, so the gradient is just dr of u squared. And I just want to make a comment. So let's start trying to think about what are the what do solutions look like, or what do admissible, remember this is u, I want to think of this as this angle. So if I have finite energy, I need this this part of the potential energy to be integrable. And since I have a 1, this is r dr here, we're in R2, and I have 1 over r squared here, so I have a 1 over r singularity at 0 at an infinity. So this means if u is to have finite energy, u has to tend to a multiple of pi as r goes to 0 or as r goes to infinity. So right, I have to tend to a 0 of sign for u to have finite energy. In practice, what this means is that at r equals 0, I have to be either at the North Pole or the South Pole, and same with as r goes to infinity. So, and this equation has the only possible scaling for this equation is the following. If I have a solution u as a function of t of r as a solution, then so is u of t over lambda r over lambda, where lambda is a positive number. And the well-posedness of this equation goes back to the 90s. It was understood by Chattat Talved-Arzadeh, who proved other things as well in this very nice paper from '94. But let's now talk about these stationary solutions to this equation. So again, the constant solutions, so the vacuum solutions, are just if I have have finite energy, I could just be a multiple of L pi. These are the vacuum solutions, the constant maps. But I also have, as I mentioned, I have non-trivial harmonic maps, and these are some of these are preserved under equivariant symmetry. So in particular, for each k, there exists a unique, up to rescaling it, of course, non-trivial finite energy harmonic map, q of r, which is just given by 2 arctangent of r to the k. So when k equals 1, you see this is just 2 arctangent of r, which is the polar angle of just a stereographic projection map. So when k equals 1, the first non-trivial harmonic map is just the identity map of R2 with stereographic projection. Okay, so this is, but again, I'm going to study just in these coordinates. So in this setting, q starts as r tends to 0. This looks like 0. This tends to 0, and as r tends to infinity, q tends to pi. And I obtain a 1-parameter family of harmonic maps by rescaling in each equivariance class. And these are energy minimizers. Well, they minimize the energy for each fixed k. They minimize the energy amongst k equivariant maps, amongst those maps which connect the North Pole to the South Pole, right? So as q tends to pi at infinity, this means I connect the North Pole to the South Pole. So these are bona fide energy minimizers. They minimize the potential energy. So these are static solutions, and again, I told you I was going to study asymptotically stationary solutions. So since they're static, they're also asymptotically static. But are there more? the claim is, as we'll see in the talk, is that yes, there are more, and the candidate for an asymptotically stationary solution is what I'll call a bubble tower for this equation. So I'm going to make a definition. We'll say that U, a solution, is a strongly interacting in-bubble tower if it admits a decomposition into superposition of harmonic maps living at different scales. So so if I can find n continuous functions lambda j, which I should think of as being dynamically a dynamic scaling parameter, so that U is, I'll draw some pictures on the next page. So that U is equal to a superposition of alternating harmonic maps. I'll call these bubbles. See, they're dynamically scaled. Q is a function of R, but it's being rescaled at lambda j of t. So this is a nonlinear equation. So these are a superposition like this is not a solution. So there has to be some error in order for this to be a solution. But I require that G in the energy space and dt of U tend to 0 as t goes to infinity. So this error washes asymptotically just a superposition of bubbles. And the bubbles are asymptotically orthogonal in the sense that their scales are separating as t goes to infinity. So the ratios of the scales tend to 0. And this normally uses H norm. This characterizes the energy space. It's not just the H.1 norm, but it has this. This is a two-dimensional space, so I have this Hardy component as well. This is a natural norm for the equation. Okay.
Could I ask a question?
Of course.
Can you actually construct, for example, the possible case like, say they are separated, either they somehow far apart from each other, the scale may be similar, or maybe both are small scale, but they separate maybe not far distant, like a unit distance away. The lambda i's are compatible, but they are separate. Yeah, different points, for example. But I think it's not radial symmetry case, right?
Yes, I see. So if I have outside of radial symmetry, can I put bubbles at different points in space, but at possibly different scales? So there are static solutions, it turns out, that look like this. So I should just think of the harmonic maps as being rational functions in the complex plane. And so then you can think of a rational function that has mass is centered at different points, or rather that vanish at different points of the plane. Vanishing would mean that
I understand now, because you look at this symmetric case. So
in the symmetric case, now I'm going to think of the bubbles as being concentrating on top of each other. So they're at the same. They're all at the origin. They're all centered at the origin, and they're living at these asymptotically orthogonal scales. There's much more that goes on outside of symmetry. So I can now think about that. You can think about bubbles that are dynamically moving around. And this is almost completely open. These questions. There's work in the mathematical physics literature, but not much work with or zero work, in fact, with dynamically moving bubbles in outside of symmetry case. Does that make sense?
Yeah.
Meaning of the -1 to the j.
Okay. Yes. So these. So let me draw a picture on the next slide. So these -1 to the j, these bubble alternating between connecting the North Pole and coming back to the South Pole. And you could think of bubbles. You could think of superpositions without this -1 to the j, right? I could see bubble, 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 bubble. And I'm making an implicit claim in this definition that such things don't exist. It turns out. So you're right that you should be. It looks like I'm assuming something here, but it turns out that there are probably no solutions like of the type that you mentioned. So here's what the pictures look like, and here's what this is maybe easier to keep in mind. So when n equals 1, just a one bubble tower is these are completely classified. This is just a unique harmonic map up to scale, of course. n equals 2, I should there's two bubbles. So what the polar angle looks like is I have a map that connects from the North Pole to the South Pole, and then unwraps again and goes back down from the South Pole back up to the North Pole. So this lump here is actually a two bubble, what a two bubble solution looks like. For three bubbles, it I connect North Pole to South Pole to North Pole back to South Pole again. I mean, you should think of it as a map itself as wrapping, unwrapping, wrapping.
But Andrew, I have a question here. Can you put bubbles at the North Pole and the South Pole that don't unwrap?
That don't interact? No,
don't unwrap, because here you are unwrapping.
Yes. So I should I should think of the picture as being like this. So a bubble and then another bubble, like this. And it turns out that so I'm gonna try not, you can't have just a solution like this. So these things are gonna move. And it turns out if you think about the case that you mentioned, that the reaction is, the interaction between such bubbles is repulsive. And the structure sort of disappears if you start off with a configuration like that. So this is why I put this alternating sign with wrapping, unwrapping, wrapping, unwrapping, is that this is somehow the only.
So just to pick that up a little more, if I understand correctly, that at the end of the day, the scales have to be, it's besides being separated, you're going to have to choose the scales just right.
Exactly. Yeah, the scales are going to be, so I'm going to try and reduce this, it turns out, to some type of in-body problem. And the scales.
And you're going to have to avoid, I mean, you want it to stay stationary asymptotically for all time. So then even a small repulsion or a small attraction could mess you up.
So they're not. So they're in fact going to be attractive, and so they're not going to move, but they're going to. One of them is going to concentrate. If it turns out if I have repulsive interaction, then the structure will somehow be destroyed. So I'm gonna wanna the only way for me to get a solution, since a configuration like this isn't a solution on its own, there are no static solutions, is for the scales to behave like this ratio to go to 0. And it turns out that this will require some type of interactive attractive interaction between the bubbles. I think it should clarify in the two bubble case in a minute. I'm going to try and show you guys the ODEs. Okay, so yeah, so I've taken some liberties in this definition. I guess because at this point I know what I'm looking for. But you're right. At the moment, I haven't given a lot of justification for why I should only consider configurations like this. Okay, so just to clarify this, why I've now I started talking about asymptotically stationary solutions. It turns out it's not so hard to show that a wave map is asymptotically stationary, so it has vanishing kinetic energy if and only if it's such a strongly interacting in bubble tower. And I won't go through the proof, but this is somehow the proof is an analysis of Pellet-Schnell sequences using method of profile decompositions, using this fundamental result of Bahuri-Girard. So if you believe me that asymptotically stationary is equivalent to being one of these in bubble towers, then my goal now is to find and classify all possible in bubble configurations. And in this talk, so we've made some progress towards this. I'm going to present a complete solution in the case n equals 2. But keep in mind that there's a broader program in mind. And let me state a theorem. So there's work of Jendrej and then joint work with most of the theorem, or the last two components of the theorem are joint with Jacek Jendrej in 2018, 2020. So this is a classification of all two bubble wave maps, and for the complete theorem, I'm going to restrict to the equivariant success k bigger than 3, and in the next slide, I'll tell you what's known about k equals 1 and k equals 2 as well. So on the one hand, there's existence. So there exists a solution, I'll call this U sub 2. It's in fact an H2 solution. It has some additional regularity, better than energy class. In fact, we conjecture it's smooth. So that U decouples into, it's a two bubble tower. So it looks like Q sub lambda of T, this means Q at scale lambda minus Q at scale mu plus an error term G. The error term is vanishing in energy. The kinetic energy of the solution is vanishing. So this is a asymptotically static solution. And the rates are explicit. So lambda T tends to 0 as T goes to infinity. And it looks like T to the minus 2 over K minus 2 with an explicit constant in front. And then mu stays at scale 1. So tends to 1 as T goes to infinity. So what the solution looks like is one static bubble and one concentrating bubble. So moreover, we have a uniqueness result. So this is in fact the only two bubble configuration. So UT is unique, the unique two bubble wave map. Of course, up to the symmetries of the equation. So up to sign, so I'll call this this solution like this, a bubble anti-bubble. You can have anti-bubble bubble as well. This is just time, just changing the sign in front of the solution. Time translation equations, time translation invariant, scaling. What I mean by this, if I have any other forward in time two bubble, of course I can time reverse these as well. Two bubble, then I can find a sign, a scaling parameter, a fixed scaling parameter mu naught, and a time t naught, such that U of t is equal to a rescaling and time translation of this of the two bubble that's constructed in part 1 of the theorem. And then moreover, you can ask what happens to this solution. This forms a two bubble in forward time. You could also ask what happens in negative time. So what happens is that if I reverse time of this solution. So in forward time, if you think that there's a two bubble, the bubbles are interacting. One of them is staying static and the other one's concentrating. You can think of the one as pushing the other one to concentrate. And in reverse time, the outside bubble is static and the inside bubble is expanding. And at some point they reach the same, their scales become comparable, right? Or their scales become comparable. This is the evolution of the scales. So you could think of at some point the bubbles collide and scale. They have some comparable scale. And what happens is that the collision of these two bubbles completely annihilates the two bubble structure. And the solution disperses. It becomes free radiation in opposite time. So you have, this is called a collision analysis, and in like colloquial terms is referred to as the collision of these two bubbles being inelastic. The bubble structure is destroyed by the collision. The solution completely disperses in opposite time. And let me make some remarks. So in addition to this, note, since this guy has vanishing kinetic energy and the two bubbles become orthogonal, the energy of such a solution is exactly twice the energy of a bubble. And the map it's a bubble anti-bubble, so the map is topologically trivial. And it turns out that we can also characterize any other topologically trivial solution with this energy. The rest of them scatter in both directions. So you can think of this as a classification of all the threshold behavior for such maps, because it was known previously that if I have energy less than twice the energy of Q, so not quite, and I'm topologically trivial, so I don't have quite enough energy to form a two bubble configuration, all such maps have to scatter as well. This last component of the theorem, the collision analysis, this is kind of a mostly open question for solution for PDEs emitting solitons. So outside of the integrable setting, it's kind of so for example, for the sine-Gordon equation or an integrable KdV in LS, you have inelastic collision of solitons. Solitons kind of pass right through each other. But it's expected somehow that outside of the integrable setting, collisions are generically supposed to be inelastic, so that any collision of solitons produces some energy is lost to radiation. As far as I know, there's very little rigorous work in this direction. There's lots of work in the mathematical physics literature, numerical experiments, but there's some papers in the mid-2000s by Martel and Merle for the quartic GKDV, and they have a recent paper about the NLW and 5D. These are somehow, these KDV papers are somehow in a perturbative regime. There's a small soliton or a slow soliton and a fast soliton. In our setting here, you could think of the evolution of this in forward time as a two-bubble structure. So remember, it scatters in negative time. So it's pure radiation coming together and forming a two-bubble structure. So it's a two-bubble structure emerges from pure radiation. I think as far as we know, this is the first such result. And the theorem, I stated before that this the theorem for equivariance class is k bigger than 3. The theorem holds also for k equals 2 and k equals 1, except for the uniqueness, the uniqueness part, which is still open for technical reasons. So k equals 2, the existence and classification and collision analysis was Jendrej in 15 and Jendrej with me in 2018. And the k equals 1, a postdoc at MIT handled the k equals 1 case in 2018. And there's two bubble infinite in forward time, and there's no two bubble in k equals 1. In fact, the solution blows up in finite time. Okay, so I want to kind of keep thinking about how to, or keep going back to this dynamical picture that I started in the beginning. How should I think about this, these solutions? So the solution, the two bubble, yields a two-dimensional forward invariant manifold. So I'll call this, so I'm going to try and think about this dynamically a bit. I'll call this M2S. I'll explain S in a second. And the one way of parameterizing the manifold is just by the time translation and by the scaling parameter. So this is a 2D invariant manifold. We proved H2 regularity as I mentioned for this manifold. However, we expect it to be smooth. There seems to be no obstruction to smoothness. And how to understand this? Well, consider any two bubble configuration like this. So I have a bubble and an anti-bubble. And lambda mu are both positive. Bubble at scale lambda and an anti-bubble at scale mu. This object is not a solution. It's not a in fact it's not a critical point of the potential energy, right? Because it's a nonlinear equation. I can't just superimpose two solutions and obtain a solution. But I can somehow think of it as an ideal critical point. It becomes a solution if I could have the scales be infinitely separated. So if lambda over mu was equal to 0. This is this notion. There's a notion. It seems this beautiful notion from the calculus of variations, I think developed by Abbas Bahri in the 80s, of this notion of ideal critical point at infinity. So this is not a true critical point of potential energy, but it's in some sense I can think of it as such. In fact, I can define a distance to this ideal critical point. So I say I measure the distance between U and this not invariant manifold Q lambda mu, Q2 I'll call it, as just taking the nth over all possible scales of the difference between U and a point on this manifold. I require that I have small kinetic part of this vector U, and I include a penalization factor for the scale. So I want this distance is only small if the scales are well separated, if lambda over mu to the k, and this is a normalization factor, is small as well. So this gives a distance to this ideal critical point at infinity. And I want to think of these two bubble solutions, this manifold, this invariant manifold that we constructed, as the stable manifold of this ideal critical point at infinity. So I'll try and explain this in a second, but by time reversal, I obtain then the unstable manifold for this ideal critical point at infinity. So this is the picture I want to emphasize, and the theorem, a reformulation of at least of part of the theorem, the forward in time theorem, is that I have a solution and with distance to this ideal critical point tending to 0 as t goes to infinity, if and only if I'm on this on the manifold MS2. So this is a reformulation of the theorem, of part of the theorem, including the uniqueness part. And this collision analysis, we in this dynamical viewpoint, the collision analysis that we performed showed that I can't have any homoclinic orbit. I have, in fact, the manifold is heteroclinic in the sense that I connect two bubble at t is plus infinity with just pure radiation at minus infinity. So I have two different, I have an orbit connecting two different types of dynamical behaviors. Okay.
So this is just a one-dimensional manifold?
It's a two-dimensional manifold. It's a two-dimensional manifold. I have you can think of it, the two dimensions are the different scales of the bubbles.
Lambda and mu, I see.
Yeah. And in MS, so this is one choice of coordinates on the invariant manifold is just time translating, taking my one solution, time translating or rescaling it gives me two dimensions for the invariant manifold here.
Okay.
And then you can think of with the setting, you can think of these this typical picture here. If I think of Q2 as this formal critical point, I'm going to draw this two-dimensional object. This is a single dot on this page, and I have stable, unstable directions here. So this is MS in the unstable manifold here, and stable manifold. Then, although what I've constructed I've constructed this object, but then this tells me as well about solutions nearby, right? If I think of a small neighborhood of this ideal critical point at infinity, the only way I leave this small neighborhood is by following the unstable manifold out of here, right? So I go out like this. And what this tells me is if I take any solution, any initial data inside here, I have two possibilities. Either I stay close to Q2 for all times, or I run out along this unstable manifold. And if I run out along the unstable manifold, I know that this solution, so I know that the objects on this manifold have to scatter in the opposite direction, right? I become in this setting, in forward time direction, I become a scattering map. So scattering is an open condition. So I know that anything that leaves the neighborhood of this critical point must also scatter in the opposite direction. So it just as in dynamical systems, classical dynamical systems theory, understanding these objects is important to understanding the flow, the nearby flow as well. Okay, so if it's okay, I'd like to try to make some comments on the proof, or at least some aspect of the proof. I wanted to discuss this the proof of the uniqueness part of the theorem. And I only really know of two ways of proving uniqueness to solutions to a PDE. One is via contraction mapping principle, kind of, and where uniqueness kind of comes with the argument, and the other is maybe more of a principle, the principle of weak strong uniqueness. And our proof in this case follows or doesn't follow exactly, but builds on an idea from Struve, an older paper from maybe about 20 years ago, proving uniqueness of weak solutions to critical wave equations. So my idea is that I'm going to construct a single solution. So what I mean by weak strong uniqueness is the following: I'm going to construct a single solution, and I'm going to prove as many properties about this as I can. In particular, I'm going to prove that it's smooth and has nice regularity properties. So I'll construct my one strong solution, and then I'm going to view any other solution as a try to view it as a perturbation of this strong solution I know a lot of properties about. So I'll mention what the idea of Struve is in a minute, but this step one is to construct a single solution. I don't have time to tell you exactly how this happens. So there exists a solution, you C for constructed, the following property with the following dynamical behaviors are the ones that I claimed existed. I can claim that we can construct such an object. We can prove more about it too. There's I can expand this error into profiles. In fact, I can obtain the kind of next order behavior of these dynamical behaviors, and also prove H2 type estimates. And so let's accept that we have a single solution. And then I want to note some properties. One is that the scales are nice. If I can get nice control, I get nice control over the derivative of lambda. In fact, lambda is a monotonic function of time. Its derivative is strictly negative. So that means I'm going to reparameterize time using the scaling parameter. I'm going to put some nice dynamical coordinates on this manifold. So lambda c is monotonic. So I'm going to reparameterize time as t is equal to lambda, the constructed dynamical parameter, lambda c inverse of sigma. And then I'll call u mu sigma. U and sigma will be my new coordinates on this manifold. So it's the constructed solution. Time is reparameterized, right? So now it's a function of sigma. And I rescale the scale mu. So these are dynamical coordinates on the manifold. And now let u be any other two bubble in forward time. So any other solution that decouples into it. It's as in the definition of a strongly interacting two bubble tower. So what this means is the distance to this ideal critical point at infinity tends to 0. And then it's natural then to project u onto the stable manifold. So I'll find I can find functions sigma of t and mu of t, where I write u of t is equal to capital U, which is my constructed solution of these new coordinates at coordinates u and sigma, plus an error. And now the game is going to be, I'm going to want to show, and I said project, I'm going to pose some suitable orthogonality conditions as well for G. So the game will be, I'd like to show that G is equal to 0 at least one, for at least one time t, because then I've shown that my solution intersects with this manifold, and so uniqueness of the flow, then I have to stay on the manifold for all time. So I want to find a single time t for which G vanishes. And there's the very nice idea of Struve I mentioned is I want to obtain some a priori information about G. And I can do so just by Taylor expanding the energy and noting the following easy fact: if I have two solutions with the same energy, they have the same energy. Right, so the energy of capital U is equal to the energy of U, which I've also written as capital U plus an error. And now I Taylor expand, do a formal Taylor expansion of energy. I get energy of U again, so I can subtract these terms on both sides. I get a linear term in G. This is the crucial term somehow. And then I get quadratic terms in G or higher. So the second line, this quadratic, so the first line I can subtract from both sides, as I said. This second line is quadratic in G. In fact, by the choice of coordinates I made, I put some orthogonality conditions so that this is bigger than or equal to a constant times the energy of the energy norm of G. This is coercivity due to the orthogonality conditions. But then from this equation here, I obtain, and these lower order terms I can absorb into this term, I obtain an inequality. So 0 is bigger than or equal to this linear term plus some constant times the square energy norm of G. And if you look hard enough at this, you see that this is some type of instability. This gives me some type of instability. So I in particular, this needs to say, I have some, this is giving me some information about this linear term. So, and what I'll show is, I know that G should tend to 0 as t goes to infinity, and that this inequality is going to prevent this from happening unless G is identically equal to 0. So here now we need to depart significantly. Struve's idea has this idea of expanding the energy, and then his analysis also hinged on analysis of the linear term, but now at this point we're going to depart significantly. So So how do I show that G should be 0? Well, I'm going to try and understand the dynamics of this linear term. And I note that this looks a bit scary, but this is a natural object. By my choice of coordinates sigma and mu, I see this d, this Fauché derivative of the energy at this point, u mu sigma, is nothing other than some renormalization. This is important, in fact, what lies here, but of J composed with d sigma of capital U. So this is just, so mu and sigma are my coordinates on the manifold. D sigma of U is a tangent vector, right? So here's d sigma of U, here's the manifold, here's d sigma of U, and this is just rotation of the tangent vector by 90 degrees. So this is now projection of G onto this vector. So I'm kind of measuring measuring how much of G lies in this direction, and this term is now going to be deeply related to what are called the modulation parameters mu and sigma, the dynamics of these modulation parameters. Is there a question?
Actually, I do have a question. So in your picture, you have a hyperbolic kind of picture with no neutral directions, right?
Yeah.
And the absence of any neutral directions is somehow hiding inside what you're talking about now.
Yeah. Yeah. The picture I drew should it should be taken with a grain of salt a bit. But yes, but the short answer to the question is yes. There's an absence of neutral directions. Yeah.
Okay. Please go ahead.
Yeah. Okay. So I'm going to try and analyze the dynamics of this linear term. Since I've worked so hard to understand the solution I constructed, I know precisely how this normalization factor behaves. It looks like sigma to the k over 2 times some explicit constant. And so now I'd like to just naively differentiate this object and try and use the equation at some point, differentiate this object, use the equation at some point, and now and analyze its dynamics. So it turns out that this is too naive, of course, but you can roughly do so. So meaning I can understand. So I'm going to introduce some corrected variable. I'll call this b of t. It's precisely the thing I'm interested in, renormalized, so that I'm looking just like this d sigma of u. And then I need. It turns out if I differentiate this object, I'll get some terms. I want to prove a monotonicity formula for b prime, and it turns out that there'll be terms that look like of critical size but indeterminate sign. But I know that I can build some ad hoc correction to such terms. So I won't totally explain this, but this is we call this a localized virial correction. And one can build such corrections, it turns out, in different contexts. It seems these terms that fail to have good signs are somehow arising via the symmetries of the equation. Here, the symmetry is scaling symmetry, and so I can build this correction using the generator of scaling. This lambda naught is RDR plus 1. This is the generator of L2 scaling in 2 dimensions. And I put quotes because it's not quite this. I have to localize this to scale mu sigma. Just localize this. So this correction is small, right? So here I see this term looks linear in G. This term is quadratic in G. I should think of G as being a small thing. So the correction is small, but the point is now the derivative of this correction will be big enough to cancel terms when I take derivative of this. And this idea is not new, but there's some newness of it in this context. So there's a very nice paper of Pierre Raphael and Jeremy Sheftel in a different context where they have such a corrective term like this. So in the context of an energy functional, and then we've used such corrections having this as our toolbox has been quite helpful. So the heart of the matter is on the one hand, B, from the inequality I wrote from the Taylor expansion of the energy, I get some estimate on B. I get a lower bound on B. So B is bigger than or equal to this positive object, which I'll call A. And I have this sigma to the minus k over 2, where sigma is a small number, so this is very big. So this is much, much bigger than norm of G squared, B of T is. But on the other hand, I can prove some estimate for B prime. So B prime, I have some differential inequality for B prime. And if I put A and B together, I can show that that B must grow, which is impossible since I know that B should tend to 0 as T goes to infinity. B looks like a norm of G, which should tend to 0. And so this gives a contradiction unless G equals 0. So this is how uniqueness is proved. So this is one aspect of the theorem, and I think I'll probably already out of time, but stop there.